In this video, we will look at Kirchhoff's rules. We will first look at the junction rule, which tells us how currents behave in a given circuit. Next, we shall look at loop rule associated with potential differences across different devices in a given circuit. We will show how to analyze circuits using these rules in order to solve for electric current, potential difference, and unknown resistance that appears in a given circuit. We will then present a few solved problems to highlight these steps. Let us first define what a junction rule is. Assume that you have the following circuit. A very simple circuit with one battery and two resistors, like that. Now we know this is a positive terminal and this is a negative terminal, so the current goes like that. So let's say that current that's coming out of the battery is I1, and we know that it's going to split into, let's say, I2 and I3. I2 will go into the resistor little r, and I3 is the current passing through the resistor capital R. Let's concentrate on this junction right there. So if we retrace that junction, that is what you get. So that junction in blue is right there. So again, relabeling the currents, I1 that way, I2 that way, and I3 that way. Junction rule states the following. It says total current towards a particular junction equals total current that is going away from that junction. So applying the statement to this junction right there, we can simply write the total current towards the junction. In this case, it's quite simply I1. So I1 equals the total current going away from the junction. In this case, it's I2 plus I3. That is the essence of junction rule. So junction rule implies there cannot be any charge buildup at that junction. Let's look at the following simple circuit. So you have a circuit with two batteries, let's say EMF E1, E2, and two resistors with resistance R1 and R2. So in this case, let's label the currents. So let's take that current to be I1. Now you will also have another current coming from the second battery. Let's call that I2. And I3, which must be going away from that particular junction. So you have two junctions here. Let's call this junction Junction A and Junction B. Let's look at Junction A and apply junction rule. So the current towards Junction A is I1 plus I2. That is the total current that is going towards Junction A. And the current that is going away from Junction A is just I3. And that is the junction rule applied to this Junction A. What about Junction B? So this current is still I3. The current that ends up in the battery, the negative terminal of battery with EMF E1, will again be I1, and the current here is I2. So applying junction rule to Junction B will give you the following. Current towards Junction B is only I3. The total current away from Junction B, there are two in the sum, which is I1 and I2, so you just sum them up. And you get the same equation as that. Next, let's look at the second Kirchhoff rule, namely the loop rule, which says the algebraic sum of potential differences in any loop of a circuit must be 0. So what does that mean by loop in a circuit? So in this diagram, you have a circuit, a very simple circuit, and there's just one loop. The loop begins, let's say, from the battery, goes like that, and comes back to the battery. So you can create the loop in a counterclockwise direction. So how many potential differences will there be? Well, there are two. The first, as you go around the loop, you will encounter the battery, and you will traverse the battery from the negative terminal to the positive terminal, creating the first term. And as you go across the resistor completing the loop, you will traverse through the resistance like that to the right-hand side, thereby completing the loop. So there are two terms. The first term is due to the battery. The second term is due to the resistor, the potential difference across which is I times capital R. What about this circuit? Generally, we can create three loops. The first loop in the upper sub-circuit of this larger circuit, let's call that loop 1. The second loop will go like that, so that is loop 2. The third loop can be constructed by considering the outer perimeter of that circuit. Let's call that loop 3. If we consider loop 3, how many potential difference terms are there as you go around loop 3? The first one is, of course, we can start with this battery with EMF E1. So the number of potential differences, E1. And then you come downwards all the way and you hit the resistor R3. So that would be the second term for the potential difference. Let's say the current through R3 is I3. So the potential difference there will be I3, R3. Then you go back as you complete the loop. You will go across the resistor R1. And that's going to give you the third term. Let's say the current through R1 is I1. The resistance is R1. And that is the third term. So loop rule says when you add these three terms, namely this, and this up, you should get 0. For that to happen, some of the terms must be positive and some will be negative. And we shall look at the sign convention to determine that in a minute. What about loop 2? As you go around this loop, namely loop number 2, let's say you start from the battery E2. So the number of potential difference terms will be the first one E2, and then you hit the resistor R3. Let's say the current through it is I3, so I3 R3, and then followed by the potential difference across resistance R2, which is I2 R2, where I2 is the current through R2. So when you add this term to that term to that term, Kirchhoff rule says the sum must be 0. Let's look at sign conventions associated with loop rule. Now, if you traverse across a resistor in such a manner, in the same direction as the direction of the current, then the potential difference that you compute by sign convention must come with a negative sign, namely like that. However, if the direction of travel is opposite to the direction of the current, then the potential difference across this resistor will assume a positive sign, like that. So that is the sign convention associated with potential difference across resistor when applying Kirchhoff rules, namely loop rule. Next, sign convention for battery. If your loop is, let's say, like that, so you are traversing this battery in this direction from the positive terminal to the negative terminal, then the potential difference term for this particular battery will assume a negative term. Namely, it will be minus E. If the battery that you are going across is connected like this, you're going from the negative terminal to the positive terminal, then the potential difference term contributed by this battery will be positive, namely positive E. So those are the 4 sign conventions that you have to remember when applying Kirchhoff rules to analyze a given circuit. Let's look at the particular problem. Find the current I in the circuit below. So let's use the loop rule to analyze the circuit. There's only one loop, the current is going from the positive terminal of this 12-volt battery to the negative terminal of this 12-volt battery. So as shown here. So that is what we want to determine. So since here we have decided to go clockwise, let's start from the 12-volt battery. So as you traverse across the 12-volt battery, we'll pick up the first term. Remember, from the sign convention, you're going from plus terminal to the negative terminal. So that's going to be minus 12. Next, you will go across the 7 ohm resistor. The direction of travel is opposite to that, the direction of current. So according to our sign convention, the potential difference term will be positive, I times 7. Next, the 4-volt battery. You're going to go across it like that, from the negative terminal to the positive terminal. So that's going to pick up a plus term, plus 4, that is. Now the 4 ohm resistor. You're going across the resistor in a direction opposite to that direction of the current. So that's going to give you a plus term, plus I times 4. Likewise, the 2 ohm resistor, you're going opposite to the direction of the current. That will contribute I times 2. And finally, the last 2 ohm resistor will give you another I times 2, positive term that is. And all this will sum up to 0, which will give you 15I equals 8, and therefore the current is 8 over 15 ampere. That solves the problem. Problem 2. Find the unknown current I that is represented here, the internal resistance R, the internal resistance of this 12-volt battery, R, and the EMF E, which is this unknown EMF E, in the circuit below using Kirchhoff's rules. Let's determine the unknown current I by using the junction rule that we talked about earlier. So which junction should we apply this rule to? It's that junction. You immediately see the current, the total current towards that junction is quite simply that I right there, which is what we want to find. The current away from that junction, there are 2 terms. One is the 1 ampere and the other one is the 2 ampere. Note, the 2 ampere is going downward like that over there, and 1 ampere is going to the left. So the sum of that is 1 plus 2, which is 3 ampere. So that is the answer for the unknown current I. Next, let's try to calculate the internal resistance R. Let's use that following loop, the outer circuit loop, like that. And let's go in that direction. How many terms would you encounter in your loop rule? The first term is due to that, the second term is due to that, and the third term is due to that. So you are going across the battery from the negative to the positive terminal. So that's going to pick up. So we are applying loop rule here, positive 12, the first term. The next term is the potential difference across this internal resistor. And you're going in the same direction as the direction of the current, so that's going to pick up a negative term, IR. And finally, the 3 ohm resistor, same direction as this direction of that current, and that's going to give you 3 times 2. And there are no other terms until you get back to the battery, so the sum must be 0. We know what I is. I is 3 ampere. We have just computed over there, and we can determine the internal resistance, which is 6 divided by 3, and that is 2 ohm. And that is the unknown internal resistance, little r. To determine the EMF E, we can use that loop. Going across that unknown EMF will give you positive term. Then going across this resistor will give you another positive term because it's opposite to the direction of that current. It's 1 times 1, that is the potential difference across that resistor, so that is plus 1. And finally, completing the loop, going across the 3 ohm resistor in the same direction as the direction of the current will give you a negative term. The potential difference is 3 times 2, that's 6, and the sum must be 0. Solving for E, we get 5 volts, and that solves the problem. Thank you for watching.